In a parking lot at a government lab near Washington are the remains of the World Trade Center. 200 tons of steel salvaged from ground zero. Just a tiny part of the original million-ton structure, but maybe enough to solve a mystery.
Obviously it was damaged by the impact of the airplanes, but it stayed up for quite some time afterward and actually collapsed due to the fire. So we want to investigate precisely what happened, materials, design, what was the total interplay so that we can have impacts on the building codes and designs of buildings in the future to see if there's anything that should be avoided.
Tim Fakey is a metallurgist at a U.S. government lab called the National Institute of Standards and Technology. NIST is investigating the collapse. And to find out why the towers came down, the researchers are putting them together again in computer simulations. Engineers call them models.
We mathematically, in a computer, construct each piece, all of the connections, as close to reality as we can, and then we can take something else like an airplane or a fire to affect that structure in the computer and see if we can recreate what actually happened that day.
To build a realistic model, they have to analyze the actual steel of the Twin Towers. That's because the World Trade Center was primarily a steel structure.
Okay, what we have here is a diagram of the damage to the side of World Trade Center 1 from the first airplane, where you can see where the wings went in, where the two engines were in the fuselage, and mapped around this are the pieces that we've identified that we've recovered and physically are here on site that we're studying. And the most interesting of all these pieces metallurgically is this one here, because it was directly impacted by the airplane at 500 miles an hour. And this particular piece we happen to have standing up right here. We call it M27. It spanned the 93rd to the 96th floors of World Trade Center 1, and the plane actually impacted on the very topmost portion. Now, when we look at this from a failure point of view, if we look at the fracture surfaces up there and look at the surface features, we can tell how the steel behaved being hit by an airplane at 500 miles an hour. That information, coupled with the tests we're doing, feeds information into the models.
Tim's task is complicated because of the condition of the steel, twisted by the fall and heated by the smoldering fire at ground zero. To find out what damage was caused by the plane, and only by the plane, he turns to image analysis, enhancing videos and photos taken on September the 11th.
And from this information, we can map out, say, a specific column that we know that we have. For example, M27 actually belongs right here. And by taking a closer look at that, you can map out, here's where M27 should be. By comparing this image to what we have out in the parking lot or out in the other building, we can determine that these two failures, the top of this column and this one here, were caused by the airplane's impact, and the fact that this column is currently missing out there was due to the building's collapse.
Another factor that complicates learning about the metal is the fact that the World Trade Center was built with 14 different types of steel with very different properties. To find out how all the various kinds of steel behaved when the jets crashed into the towers,
3, 2, 1, 0.
NIST researchers are smashing tiny samples of the steel in a device called a Kolsky bar. An air gun fires a projectile at a metal bar, and pressure waves travel down the bar and crush a piece of steel that's only slightly thicker than a dime. Sensors record the amount of stress that each piece is subjected to, while a high-speed video camera records the damage. It all happens in 1/7,000th of a second. Meanwhile, at NIST's Building and Fire Research Lab, researchers are gathering data on what happens when a typical World Trade Center workstation is doused with jet fuel and set alight. The workstation is accurate right down to the paper, furniture, computer, and wall coverings. That's information Kevin McGrattan can use. He's modeling the spread of the fire in the towers. He has rebuilt individual floors using floor plans supplied by former tenants.
Here we are on one particular floor, and you can see the outlines of the furnishings, and I'm superimposing the numerical grid. You could think of this numerical grid as the Lego blocks that make up the tower. Nothing in the tower can be shown in finer detail than a single Lego block, which might be this big for these types of calculations. And in each of these blocks, we assert the laws of physics, conservation of mass, momentum, and energy. And each of these blocks communicates with the one next to it. And in the end, you put it all together, and that gives you a map, essentially, of how those hot gases are moving and what the temperature of those hot gases are. We take that information, we provide it to the structural engineers, and they ask themselves, okay, how will the strength of the steel be affected by those high temperatures? And eventually they will try to pinpoint exactly what failed. What you're seeing on the computer screen here is very sanitized. But we take our calculations and we compare them with these photographs that we're seeing, and then it hits home of what really happened.
Understanding what happened will not ease the enduring tragedy, but if NIST can suggest any changes to high-rise building codes, it could save lives in the future. It's not like any other job. For Bill Pitts and his team, it's 9/11 from 9 to 5, and often longer. They watch the planes strike the World Trade Center again, again, and again. And then they watch as the buildings burn and fall down.
We've seen it so much, we've probably looked at it more than just about anybody in the world.
Pitts is a scientist at the National Institute of Standards and Technology, NIST for short. The U.S. government has asked NIST to investigate why the towers collapsed so that buildings can be made stronger in the future. Most experts agree it was the fire, spread by burning jet fuel, that brought down the twin towers. The fire heated the structural steel, weakening it, starting a catastrophic failure. But there are competing theories on how the fire affected the metal and which steel components gave way first. NIST researchers are modeling the impact of the jets, the spread of the fire, and the collapse of the towers in detailed computer simulations. To do that, they need the image analysis provided by Bill Pitts and his team.
Image analysis is allowing us to learn a lot about the interaction of the building and the airplane. The reason this is important is because it's going to tell us, hopefully, what the initial damage done by the airplane was. We hope to get insights into what the airplane itself did as it entered the building, which is going to ultimately determine what the fire growth is. It's going to determine where the fuel distribution, initial fuel distribution was in the building. And that's going to allow us to learn more about what the fires ultimately did. What we're looking at is a still frame of a video that was shot on September 11th. And the reason it's of particular interest to us is because it was shot on a tripod, which means that the image is very stable and lets us do various types of image analysis to it. So when I play it, what you're going to see is the plane strike from the left, and then you're going to be able to see all the motion associated with that plane strike. And there's a lot going on here, which includes the fires that are formed after the plane hit, the plume that's formed by the plane striking. You see it just everywhere you look, there's detail. It tells us something about what happened on September 11th to this building.
One of those details is the speed of the aircraft, something that's essential to modeling the structural damage. By taking that video, shot at 30 frames a second, and scrutinizing tiny details in each frame, Bill has come up with one of the most accurate estimates of the speed of the plane that hit Tower 2.
And the way we do it is to measure the location on the photograph of both the nose and the tail as it appears, as you can see here. And then knowing the length of the aircraft and the time it takes to move from one location to the other, that's the way we're going to determine the speed of the aircraft.
In the end, the answer is straightforward: 560 miles per hour. That same piece of video can tell Bill Pitts how the building moved during the plane strike. The image of the building, whether it's moving or not, creates a weird optical effect of curved lines on the video.
And they're due to an interference pattern that arises between the lines that are actually on the building associated with the windows and columns on the building and the pixels that are the individual elements within the camera that is taking the photograph. Those two interfere, and the net result is what you see here, these patterns passing across the building. We're going to take an initial image, which is the very first image in the video that I'm going to show you, and subtract it from all the additional images, and that's what we're showing over here And we've already done it, and that's why we're seeing black now. So when we start to play it, what's going to show up is the differences between the images. So as I play it, we'll see the plane coming in again from the left. We'll see it approaching the building. And as it enters, you start to see changes in the building almost immediately. Now, these initial changes were due to pressure changes, but as time goes by, you begin to see these lines spreading across the building. These are exactly the same lines we saw before, but they've been enhanced now because we're looking at the difference. So as the building moves, these lines show up very distinctly because the building has changed.
How far it did sway, Bill won't say. He's still working on it. But there are other details he's willing to share.
Okay, what we're showing here is the plane coming in from the left. I'm going to stop it right here. And you can see what appears to be a light appearing right in this area, while the rest of the building is still dark. What that tells us right away is that the building actually hasn't moved yet, and yet we're still seeing this light area. And what we think has happened here is that we're actually seeing pressure waves pass across the windows in the building. As a result, it changes the reflection of the light striking them. That shows up as a difference, and we can actually track the entrance of the airplane into the building in this way.
The team has used video analysis to track how the fires moved through the two towers. One of the ways they've done this is to catalog the location of each flaming window, carefully matching it with time code embedded in the videos.
What we're trying to do is learn to the highest degree possible where the fires were, how intense they were, and this is going to allow the people who are trying to model the fires, first of all, to have something to compare with, but also to have some idea of how intense the fires were so they can begin to make predictions of the temperature.
The hope is that a detailed play-by-play of the disaster will emerge from these models, pinpointing structural weaknesses in the design of the towers, and then NIST can make recommendations to the building code. Though Bill Pitt's work might actually end up saving lives someday, that doesn't make the job any easier.
You tend to put yourself there. I mean, we've seen it so much. All of us have that are doing this in this room. And it really is hard because you tend to think a lot about what the people went through that day. There's just no way to avoid it. You get used to it. You try not to think about it too much because if you did, you wouldn't be able to do your job. But it's there, and you see things, and you see certain things repeatedly, and it can be very, very difficult. And it's sometimes really, really hard to separate yourself from it, but you have to do it because we do feel the job we're trying to do is important.
Not every image makes it into the database, only useful ones do. So far, the video analysis team has collected almost 6,000 still photographs and about 150 hours of video. The job of combing through it all is far from over.